So this is the last lecture in the waves set. In this lecture, I'm going to talk about superposition and interference, and then standing waves and resonance. So we're going to start with what happens when two waves collide. Now, if you have two particles that collide, right? So say, right, I have two pitching machines. Machine A shoots a ball towards Bill, machine B shoots a ball towards Alan, but they shoot them at the same time and the balls collide, right? The balls will collide and bounce apart. They can't be in the same space at the same time, but waves can be at the same space at the same time. Waves can move through each other, right? Pass through the same place at the same time, and instead of bouncing apart, they can just move through each other. Now, when waves move through each other, we say that those waves are interfering. Right? So two traveling waves, they can meet, they can pass through each other without altering or destroying each other. And when this happens, we call this interference. And when this happens, the waves are going to obey something called the superposition principle. And the superposition principle says that when two waves are interfering, right, when two waves are passing through each other, the resultant of this, when you add them up, the resultant of this is just found by adding the displacements of the individual waves at that point. Now, in real life, this is only strictly true for waves with small amplitudes. But it's true enough of the time that it's a pretty good general principle. But the way this works, right? So imagine I have a wave moving to the right and a wave moving to the left, and they have, right, different shapes. So when these two waves, these two parts of the waves stack up on top of each other, what you see basically is they add up and you see a big wave pulse. This is called constructive interference when the two waves add up. Now, when they're exactly matched up, then we have constructive interference. But then as they move through, right, this and then this back half of the second wave are exactly the same but upside down. And as these parts move through each other, they completely cancel. And when waves completely cancel, this is called complete destructive interference. When they cancel some, that's just destructive interference. But then once it's finished, right, they come back out completely unchanged. So this is the first wave, and this is the second wave, right? So here it looks exactly the same, and again, exactly the same. So one thing that waves can do is waves can pass through each other and exhibit interference properties. And we're going to spend a little bit of time on that here, but in physics too, particularly when you get to light, you're going to spend a lot more time on interference of waves. But another thing that waves can do is waves can be reflected at a boundary, or they can be transmitted at a boundary. So if you think about, right, waves on a string, right, I have a string and I just flick it and I send this wave pulse here moving to the right at some speed v. Now, I initially flick it on a heavy string, and then I have, right, a lighter string tied to the end. And I'm going to keep the same tension in the strings. Now, we remember from last time that the speed of a wave on a string is equal to the square root of the tension in the string or rope divided by the mass per unit length. So as we move from a heavy string or a heavy rope to a lighter one, right here we have a smaller mass per unit length. As mu gets smaller, the wave speed gets bigger. So this wave here is going to get, when it gets to this boundary, some of it's going to be transmitted and some of it will be reflected. And the transmitted part is going to have a faster wave speed because we've kept the tensions the same and we made it a lighter, smaller mass per unit length string. The reflected back one is going to have the same speed as the original one because it's in the same medium, it's in the same material. And then this works the other way as well. So if I start my wave pulse in the lighter string, when it gets to this discontinuity, when it gets to this boundary, again, some of it will be transmitted, some of the energy will be reflected. But the transmitted bit, because it's going to a heavier string, is going to be going slower. Then the reflected bit comes back out at the same speed because it's in the same material. Now, in this case, my reflected pulse is flipped upside down. It's inverted. And when a wave comes to this boundary, when my wave comes to this boundary, if it goes from a large density to a small density, and remember, we know that mass per unit length is just the linear mass density. Right? That is the mass per unit length. We call that the linear mass density. So if the density where it started is bigger than the density of where it's going, right? The reflected pulse has no phase shift. It comes back out with the same orientation that it went in at. But if we reflect off from a small density to a big density, so here we have no phase shift on reflection. But if we start with a smaller mass density, linear mass density, and go to a bigger linear mass density, then we have a shift of 1 pi or 180 degrees. And we can see this, right, because here, if I start with the skinny rope and go towards the heavy rope, on reflection, this reflected pulse is flipped upside down. That's my 1 pi or 180 degree shift that happens on reflection. The transmitted pulse has the same orientation, but it's a little smaller in amplitude and it's moving slower. And again, we can see this also, right, if we're going from a lighter material, a lighter medium to a heavier medium. We can also see this if our string is fixed at the end, right? So we're just reflecting and we're not being transmitted at all. So here, my string is tied to this is the end of the string. So if I'm going from from my string to a fixed boundary, then also I get a phase shift on reflection. My reflected pulse is flipped upside down from my incident pulse. If I have a free end, right, if on this end it's free to move up and down, so here it's fixed, here the end is free, it's free to wiggle, then my reflected pulse comes back with no phase shift. It has the same orientation as the incident pulse. Now, all of this is going to be important here in a minute when we get to standing waves. So now let's go back to interference for a minute. So if I have two waves with the same frequency moving in opposite directions, so wave 1 and wave 2 have the same frequency, and as they interfere with each other, as they meet up, I see this pattern where I've essentially made the amplitude bigger, but I have, for this brief bit of time where they are exactly matched up, I have what's called a standing wave. So I have places here where the displacement from equilibrium is 0, and then I have, right, these places that are going to oscillate up and down very quickly with whatever the frequency is. And then when they're finished, they pass through each other. Now let's imagine doing this same thing, but with a wave that is being reflected at a boundary. So what I have is I have a wave interfering with its reflection on the same medium. And in that case, what we have is a standing wave. So what this is a picture of is I have a string tied, fixed at this end. And then over here we have just a little motor that's oscillating, shaking it up and down, right, at some frequency. Now, if you do this correctly, right, if you pick the frequency correctly, then what you can get is you can get a standing wave. So what happens is I have this wave being generated on this string, and the wave travels over to the end and it reflects back off. And because this is a fixed end, it's going to reflect back off upside down. And the wave that's going in is going to interfere with the wave that's being reflected. And since it's the same, essentially the same wave, right? It's a wave and its own reflection. The frequency, the wavelength, and the amplitude are all exactly the same, but they're traveling in opposite directions. And so what you can get is you get a stationary pattern. So if you watch this is a time-lapse picture. And so what you have is you have regions where, right, you can see here the string is oscillating up and down. And then you have regions where the string is stationary. There's no motion here, right, which you would expect at the end. And then, right, this has a very small amplitude and a high frequency. So you would expect at the ends, right, no motion, no amplitude. But you also have these regions here where there's no motion of the string. There's no up and down oscillation. But here I have maximum up and down oscillation. So this is called a standing wave. So how this works, right, how we want to make this is so, and you can totally do this if you get a good heavy string and, right, jiggle it up and down fast enough. Tie it at one end, so you have a fixed end, right? Here you're going to, right, shake your hand up and down so that you send a wave, a continuous wave, down the string to the end, and then it's going to reflect. And so now I have an incident wave and a reflecting wave that are going to interfere. And so what I have then is I have this stable, stationary pattern. And so what I'm doing is I'm just adding two waves, right? Here's wave one, the incident wave moving to the right, and the reflected wave moving to the left. And remember, right, this shows me it's moving to the left. This shows me it's moving to the right. And if you do the math, if I add these two waves with the same amplitude and the same frequency and the same wavelength, I get this result. And this part, the 2 amplitude, right, I've doubled the amplitude. Cosine kx is the stationary wave. That tells me, right, what the wavelength is and also where are the places of 0 amplitude. These places are called nodes. So all of these are called nodes. And where are the places of maximum amplitude? That's here. Places where it oscillates up and down. These are called antinodes. And then this term tells me about the changing amplitude. This term tells me about the frequency, right? The frequency that this part's going to move up and down with. So in our standing wave pattern, we have our nodes, which are going to be for a wave on the string, right, attached at the ends. Nodes are both ends, and then the nodes are all a half a wavelength apart because this is one whole wavelength. So my nodes are all a half a wavelength apart. And the nodes don't move, right? There's no motion of this node. This is a stationary piece of your string. And then halfway in between nodes are antinodes. And these are places where the string has maximum displacement, where the string is moving up and down at the amplitude of your standing waves, right? The intensity, the amplitude, remember intensity is related to amplitude, power per unit area. Power is energy over time, and energy depends on amplitude and frequency. So the intensity is a maximum at the nodes because the amplitude is a maximum at the nodes. So standing waves are really a fundamental idea behind how a lot of musical instruments work. So for instance, let's take the whole family of string instruments. What you're doing is you have string tied down at the two ends, and then you're going to oscillate the string somehow, either by plucking it or by bowing it, and then cause it to vibrate, which causes the air around it to vibrate, and that makes a sound. But to get particular sounds, we need to have particular standing waves. And so what wavelengths you can get on your standing wave depends on the conditions of your string, the boundary conditions. So for a wave on a string, what we have, right, so let's say I have a string that is tied down at both ends, and I'm going to, right, oscillate this end up and down at whatever frequency that I'm dealing with. So I know the wave speed is equal to the square root of the tension in the rope over the mass per unit length, right? So that is tension times length over mass under the square root. So the wave speed depends on the length of the rope, but also the wave speed is equal to frequency times wavelength. So my wave speed is determined by my setup, right? It's determined by my string, the tension in the string, and then the weight of the string, the mass per unit length of the string. And the frequency is determined by, right, how fast are you moving your hand up and down on this end? Or are you bowing it? Or are you plucking it? Or whatever is causing it to jiggle, to oscillate. So then, if I solve this for wavelength, right, my wavelength is wave speed over frequency. So I can only get, but the thing is I have a boundary conditions that I need to have nodes at the end, which means that there are only so many variations of wavelength that I can get on this string. So I can get a half of a wavelength on this string, right? So I have nodes at the end, nodes at the ends, and then antinodes, right? It's going to oscillate up and down here. And this is called the fundamental frequency because it's the longest wavelength I can get. So if I have to jiggle this with a low frequency, because again, my wave speed is set, I jiggle this with a low frequency and get a big wavelength. So this corresponds to a half of a wavelength, which with the boundary conditions that I have to have nodes at the ends. So I can get a half of a wavelength, or one wavelength, or 1.5, or 2, and so on. So I can only get particular wavelengths, and my wavelengths are determined, right? The wavelengths I'm allowed to have, and this is a series of wavelengths, is equal to 2L over M, where L is the length of my string. And the reason we say 2L over M is because the largest wavelength I can get corresponds to, right, twice the length here. So one whole wavelength here would be twice the length of my string. And then M is just a number. It's an integer. 1, 2, 3, 4, so on. So this would be M equals 1, corresponds to a half of a wavelength, which again is speed over frequency. M equals 2 corresponds to one whole wavelength, right? So M equals 2 corresponds to one wavelength. M equals 3 corresponds to, right, 3 antinodes, or 1.5 wavelengths, and so on and so forth. M equals 4 corresponds to 2 wavelengths. M equals 5 corresponds to 2.5 wavelengths, and so on and so on and so on. Now, because we know the wave speed is equal to frequency times wavelength, if you want to get a standing wave, you can only jostle this, you can only cause this to oscillate at very specific frequencies. And these frequencies are called the harmonic series. The smallest allowed frequency, which corresponds to m equals 1, is called the fundamental frequency. M equals 2 is called the second harmonic. M equals 3 is called the third harmonic. And if you play a musical instrument, then you're kind of already familiar with this, but this is the physics behind why it works that way. But we can, right, plug this into our solve this equation for frequency. So frequency is speed over wavelength, but I'm going to put this in for wavelength and then solve. So my harmonic series is going to be given by the wave speed, which is determined by the external conditions for a wave on a string, for a string instrument, is tension and mass per unit length, divided by twice the length. So this is just showing the harmonic series, right, up to m equals 4 for a particular string, right? So my m equals 1, my boundary conditions, again, remember that I have to have nodes on the end for a stringed instrument. So for a guitar or a cello or a piano, right, the string is tied down at both ends. So I have to have nodes at the ends. And so the lowest frequency that I can get is wave speed v over 2L. And again, remember the wave speed depends on the tension in the rope and the mass per unit length. So m equals 2 is the second harmonic. Now, the other thing to notice is that the second harmonic, m equals 2, is just twice as big as the fundamental. And the third harmonic is 3 times as big as the fundamental. And the fourth harmonic is 4 times as big as the fundamental, and all the way up the line. So the string, these are the resonant frequencies of the string. These are the allowed frequencies where you can get a standing wave, which maximizes the amplitude. So if you're playing an instrument, right, this is where it gets the loudest. And if your instrument is in tune, then it's going to correspond with, right, particular notes. But this is also why when you go buy new strings for your guitar or your cello or whatever, right, you buy strings that are labeled an A string or a C string or whatever they are, and they're going to correspond to different weights, right? Some strings will be skinny and some strings will be fat. And so that's your mass per unit length. And then when you're tuning your instrument, what you're doing is you're changing the tension in the string. So again, our mode number or our harmonic number is the number of antinodes, right? So m equals 2, I have 2 antinodes, but this is specifically for a wave on the string where I have boundary conditions where it is tied down at the ends. So I have to have a node at the 2 ends. You can have, for instance, with certain wind instruments, antinodes at the 2 ends. So with a flute, what you have is you have antinodes at the 2 ends, because with a flute, right, again, the smallest thing you can get is a half of a wavelength, but you're essentially capping it here because you have the free end and then here. Or you can have, like with a clarinet or a saxophone, a node at one end and an antinode at the other end. So you could get a node at one end and an antinode at the other end, and so then you can get a fourth of a wavelength. So what your harmonic series looks like depends on your boundary conditions. And we are mostly going to be focusing on waves on a string, which means we have to have nodes at the 2 ends. It has to be tied down at the 2 ends or this won't work. But for wind instruments or for other kinds of setups here, then you can have different boundary conditions where you have 2 antinodes at the ends, or you can have 1 node and 1 antinode. And then that will change the frequencies that you can get out of your instrument.